x equals to square root of x plus 4 over x minus 2. Now we see that the domain has to satisfy the domain of the square root, and also we need to make sure that the denominator will not be 0, right? Okay, so then from the top one we see that the radicand x plus 4 has to be greater or equals to 0, while the denominator cannot be 0. So then I have x is greater or equals to -4, and x cannot be 2. On the number line, I put it here. On the number line, I have to the right of -4, yet it cannot be 2. You see that? Okay, so the solution, therefore, the domain is will be -4 up to 2 union 2 to infinity. Now, this one I think is quite easy. Next, what if we have another example? This one is a bit harder. What if I have find the domain of say fx equals to square root of x plus 4 over x minus 2. So you see this time the square root actually includes the denominator. You see the difference between example 1 and example 2? Now for example 2, the domain requires us to have the radicand to be non-negative, right? The radicand has to be non-negative. So x plus 4 over x minus 2 should be greater or equals to 0. Now, but this is something we already done in our one of our take-home quiz and also in our test, that when we solve nonlinear inequality, we need to do that procedure. The first one, the critical numbers. I wonder if you remember that. X equals to -4 and x equals to second sine graph. Will give us 0, while 2 will give us undefined, right? And using the knowledge we had from last time, we see, for example, the y-intercept here when x equals to 0. When x equals to 0, then when x equals to 0, the y will be -2, which is negative. Now, and notice that x equals to -4 is a 0 with multiplicity of 1. So when we jump across that, critical number, do we keep or change the sign? We change the sign. So the idea that I taught you from Monday, that if the multiplicity is odd and we change the sign, still apply even when we have rational function. Okay. Now, likewise here, 2 is a critical number with multiplicity of 1. Even though it is on the denominator, but it is multiplicity of 1, so I change the sign. Okay, then so the solution here will be, I need positive, so it will be -infinity up to parentheses 2 to infinity. Is it okay? Now, how about composite functions? Let's say I pick questions from our book. Let's say we do number 34. I somehow think this is a question I asked you to do in class. 2.7. Is it the one?
Yeah.
F equals to okay. If this were the question I asked you to do in class, I wonder if you remember what's the final answer. Let me just do it. Give me a second. I see somebody question. Oh, give me a second. Hold on. Somebody put something on the chat, but I cannot really see it right now. I wonder why. Okay, let me know if you have a question. Okay. I don't want to be too focused on the board and then I don't see your hand or if you have a question. Okay, let me continue. Suppose I have f composed g of x, is f of g of x, which is f of x minus 5 over x plus 4. And that is, oh, this one is ugly. X minus 5 over x plus 4 plus 2. X minus 5 over x plus 4 minus 1. I have the kind of like a lot of noise from one or a couple of you. If you are not speaking, would you mind to mute your microphone? Thank you. Okay, and x plus 4. I multiply the top and the bottom by the LCD. X plus 4. So on the first term, on the top left here. Oops, sorry. On the top left here, when I multiply by x plus 4, I get
X minus 5.
X minus 5, that's right. Plus, when 2 multiplied by that is simply 2 times x plus 4.
2x.
If you want to distribute right away, go ahead.
No, it's fine. It's better like that, so I won't be confused. Sorry.
Yeah. No, that's okay. That's okay. Yeah. I mean, you are in Precalculus, so I do think that you have the capability to skip little steps here and there. And then at the bottom, oh, the bottom becomes quite nice, huh? So when I simplify it, I get 3x plus 3 over negative 9, which I think I can reduce. Let me factor the 3 first. So we get negative of x plus 1 over 3. Now, I think that part is easy. The question is, what is the domain? Now, the domain of a composite function will be the domain of the final result. In this case, the domain here is, if you notice, this is simply a linear function, right? I can write this as negative 1/3 x minus 1/3, right? Whose domain is all real number, right? However, I need to look into also the domain of the incoming function, the domain of the gx.
G.
Right? Now the domain of gx will be all real number
But -4.
but -4. All real number but -4. So I come down here, I will have all real numbers and intersect the domain of the incoming function. Then it will put us to all real number except -4. Okay, now the key is we need to take a look on the incoming function also. Now let's see. I think I have some type of problems in my old test. You can take a look in some of my old tests, but let's do this one. I wonder what example is this. Example 3, example 4. I don't even remember. Let's call that example 4. Let's say our fx be 2x minus 1 over x plus 4, and our gx be 3x minus 2 over 4x plus 5. I know it looks really ugly, but let me ask you to try this. Find this function first. Find the composition of function. Find f on both g. Then, if you have a chance, find its domain. Let me give you 2 or 3 minutes from here. Okay, let's see what we have. Well, you may not be done yet, but that's okay. I hope you already get some idea. F compose G of X equals to F of Gx. That's F of 3x minus 2 over 4x plus 5. Oh, by the way, I hope you realize that the idea of composition of function is something we already learned back in our intermediate algebra, supposedly. However, the difference between intermediate algebra and precalculus is the focus on the domain. So expect me when I ask you to when I ask you composition function, I usually also ask you what's the domain of the resulting composite function. This is 2 times 3x minus 2 over 4x plus 5 minus 1 over 3x minus 2 over 4x plus 5 plus 4. And I will multiply by the LCD 4x plus 5. And I get 2 times 3x minus 2 minus 4x plus 5 over 3x minus 2 plus 4 times 4x plus 1. That will give us 6x minus 4 minus 4x minus 5, 3x minus 2 plus 16x plus 10. That is 2x minus 9, 19x plus 18. Now then from here we see the domain will be all real numbers except negative 18 over 19. But that's the domain for the resulting function. We also need to see the domain of the incoming function. So this is the incoming function, right? The domain is all real number except negative 5, 4. So I need to also exclude negative 5, 4. Is it okay, everybody?
Yeah.
Yes.
Okay, good. I think that's all for this domain of composite function. Do you have any question, especially if you have tried to do some problem from the suggested homework?
I had a question on 25th.
26?
6, yeah.
26, let me see. Number 26. So that's from section 2.7, huh? Number 26.
Oh, sorry, I just missed the answer on the final answer.
What do you mean?
Just the is negative 18 over 19. Oh, and the input. Okay, I got it.
Oh, so do you want me to go for number 26?
Yes, that one, please.
Okay, yeah, sure. Let's see. So fx equals to square root of 3 minus x, and gx is square root of x plus 2. Now I will just do one of them. Do you want me to do f compose g or g compose f?
F of g.
Compose g. Okay, so f compose g of x will then be square root of 3. Oh, you know what? Let me slow down. That's f of gx. That's f of square root of x plus 2. And this is square root of 3 minus square root of x plus. Now, that's the resulting function. Now the domain first, the domain of the final composite function. Now this guy here has to be non-negative. Is it right?
Mm-hmm.
Okay, so let me do it here. So 3 minus square root of x plus 2 has to be greater or equals to 0. So 3 is greater or equals to square root of x plus 2. Right? And then I will square both sides. I get 9 greater or equals to x plus 2. Therefore, x is less than equals to 7. Okay,
Okay.
so x is less than equals to 7. But that's only for just the
final.
The final result. If we look at the original incoming function, we also see that x plus 2 has to be greater or equals to 0, which means x is greater or equals to -2. Now then when we combine the domain of the incoming function and the domain of the final composite functions, then the domain will be from
-2 to
negative
7.
Up to 7, that's correct. Is it okay?
Yes.
Good. Now let's go on to the next section, 3.3.
Thank you.
You're very welcome. 3.3. That's the title. 3.3. Zeros of polynomials. There are some problems. If you look at the note I sent last night, there are some problems, actually more than half of the problem from this 3.3 already doable. First one is, I will first start with the factorized form, the factor form of a polynomial. The factor form of a polynomial is a times x minus c1 x minus c2 all the way to x minus cn. Now, to be more precise, the leading coefficient a sub n will be the leading coefficient, the coefficient of the factor form also. So suppose originally we have px equals to a n x to the n. Now then, the leading coefficient we have there, the leading coefficient we have here is being carried over to this. Now, actually, if you think about it, we have the same idea when we did one of our problem in the test. I think in our test we have a function -1/2 x squared something, right? When we write it in standard form, it becomes -1/2 x minus something squared plus something. Now you see that this -1/2 as the leading coefficient is being carried through, being carried over. Okay, now that's the basic idea. So with that in mind, we can do problems from our 3.3. Let's say, for example, I pick question number 4. Number 4, we have the zeros of the polynomial are -3, -2, and 0, while f -4 equals to 16. Now we already know if we know the zeros of a polynomial, then at the same time we will be able to find the factors of the polynomial. Factors will be x plus 3. That corresponds to the zeros x minus 3. Okay. Then other factors are
X plus 2
and x minus 0, or simply x.
X.
Is it right? Now, therefore, the polynomial must be in the form of a 3, because this is degree of 3. X plus 3, x plus 2 times x. Now, then how do we find this leading coefficient a sub 3? What we can do, we plug this in. We use this. So f -4 equals to a sub 3 of -4 plus 3, -4 plus 2 times -4. That is this guy here, f -4 is 16 according to what they give us. This is a sub 3, -1, -2, -4. That's -8 times a sub 3, which implies a sub 3 is
2.
Almost right.
Oh, -2.
That's right, -2. Okay, now such that then I can go on the final answer. The polynomial, therefore, is -2 times x plus 3, x plus 2 times x. Now, with me, you can just write the final answer this way, unless I tell you to multiply them, which I usually don't have interest in. This is -2 times x times, so -2 times x, right? And then the guy here, I will FOIL that. It will give me x squared plus 5x plus 6. And then I multiply by -2x. By the way, just in case you wonder how can I do the FOIL quite fast, notice that something I expect your Algebra 1 and Algebra 2 teacher teach you. When you FOIL this, notice that the highest exponent will be x squared, right? And the constant will be 6. Is it right? Now, I think those two are, the first term and the last term are quite easy to see. The harder one is how to see the middle term. Now, the middle term always the outer, which is 2x, and the inner, which is 3x. That's how I get my 5x quite fast. You know, okay? Now, by the way, that's a skill that you need to already have at this point. And I get, let me distribute this -2x, I get -2x cubed minus 10x squared minus 12x. Now that's if you need to FOIL.
But
yeah, you need to
would
distribute.
But you say you wouldn't ask for that?
Yeah, I don't mind. I usually prefer you to write it this way. I usually ask you to write it this way. The one that I had earlier there. Yeah, okay. Now, let me do some little interruption before I go to another question. Or maybe, you know what? Let me just do it. For example, what happens if I have number 6? Number 6, it says that the zeros are -3i, 3i, and then 4. while f negative 1 is, actually you can use any number for these except 0. It's 50. Okay, so from the zeros here, we get the factors are x plus 3i, x minus 3i, x minus 4. Right, those are the factors, such that fx must be a subscript 3, because that's the degree of 3 of x plus 3i, x minus 3i, x minus 4. Then let me leave that 8 sub 3 later. Okay, that's something you can complete easily later on. But let me teach you how do you multiply this. That gives us difference of squares, right? That will be x squared minus 9i squared. Is it okay, everybody? Which will give us x squared plus 9. Any question? That's because I squared is negative 1.
Okay.
Okay. Then let's find out what is a3. F negative 1, therefore is a sub 3 times negative 1 squared is 1. This is 50 equals to a sub 3 times 10 times negative 5, which is negative 50 a sub 3. Therefore, from here I see a sub 3 equals to negative 10. So our fx, if I go back now, my fx will then be negative times x squared plus 9 times x minus 4. I actually quote it from here. Now, the thing is then, how do we apply what I taught you earlier? What do I do if I need to FOIL this? It's not too hard. This is just 2 terms times 2 terms. But let me teach you what I expect from a Precalculus students, how they will see it. We will use this skill later on toward the end of the semester. Okay, let's see. What is the highest exponent here?
Square?
No.
3?
Yeah, x cubed, right? So
Yeah.
x squared times x cubed, x squared times x is x cubed. And that's the only term that gives us x cubed, right? Now then, how about x squared? Now then, think of the combinations that give you x squared. The combination that gives you x squared, only this part here.
4x squared.
Negative 4x squared.
Yeah.
And then I have the term for x. What combination give me x? It's only this one, right? Only this one. So I will get plus 9x. And finally, the constant will be negative 36. That will give us negative x cubed plus 4x squared minus 9x plus 36. Some intermezzo. How do I expand or multiply let's say if I have 3x squared minus 4x plus 5 times 2x cubed minus maybe plus 5x squared minus 7x plus 2. And my challenge to you is how to do it fast. Now, what is the highest exponent?
5.
5. So it must be something x to the 5th, right? Now, what is the coefficient?
6.
6, because there's only one pair that gives us x to the 5th. Everybody okay?
Yes.
Mm-hmm.
Now then, let's see. The next one is x to the 4th. Now, what makes x to the 4th? This guy here and this guy here.
Mm-hmm.
Okay, so the first pair gives us positive 15. The second pair is negative 8. What will that be?
7.
Plus 7x to the 4th. Now then we go on next. After x to the 4th, we have x cubed. What makes x cubed? This guy, this guy, this guy, right?
Mm-hmm.
Okay, the first one gives us negative 21. The second one gives us negative 20. And the last one gives us positive 10. When we add them, what do we get?
31. Negative.
Negative 31. Then we go on to the next one is x squared. Now, what gives us x squared? This pair, this pair, this pair, right? Now, can you do that? So what's that?
$59.
9. That's what I get also. Now then we go on to x cubed. I'm sorry, x. The x term will have what coefficient? The one to give us x term only this guy, this pair, and this pair. Have you seen this technique before? First time?
Yeah.
Yeah, but I hope you see this is actually the extension of the FOIL method I taught you earlier. Yeah, the FOIL method I taught you earlier is like, let's say I have 3x plus 5 times 2x minus 7. So the first term must come from here, 6x squared. The middle term comes from negative 21 plus 10, that's negative 11x minus 35. Instead of writing it in 4 terms and then combine like terms, you can just do it directly. But of course, I cannot teach this method to Algebra 1 students. You know, they barely know how to FOIL, right? But once you are good with foiling, then we can go to the deeper sense of that and get this right away. Okay. By the way, back in my back in one of the class that I had a long time ago when I took the class, my teacher actually asked this type of question, and they just that teacher just asked, okay, find the coefficient for example, x squared. So instead of asking you to FOIL this long polynomial here, she just asked, okay, find the coefficient for x squared, and you need to know how to get x squared. And in this case, the coefficient for x squared is
59.
59. Great. Okay, now let's go on to the next type of question, which we already know to answer. Let's say I pick number 12. Number 12, a polynomial fx has degree 7 negative 2 and 2 are both multiplicity of 2, while zeros, so we have 7 zeros, right? We have 7 zeros. Negative 2 has multiplicity of 2, 2 also have multiplicity of 2, 0 has multiplicity of 3. Now, then once we know the zeros and its corresponding multiplicity, we can find the factors. So the factors correspond to x equals to negative 2. The factor will be
X plus 2.
x plus 2. What does the multiplicity do?
Squared.
Square it, that's right. And then the next zero,
X minus 2 squared.
x minus 2 squares, that's good. So x minus 2, oops, sorry. X minus 2 squared. And then finally,
X cubed.
Q.
x cubed. Now then our function fx must be a sub 7 of x plus 2 squared x minus 2 squared times x cubed. Okay, now they have extra information saying that f negative 1 equals to 27. So if I plug in f negative 1 here, I will get a sub 7, negative 1 plus 2 squared, that's 1 squared, that's negative 3 squared, negative 5 cubed. So that's 1 times 9 times negative 1. Do I get negative 9? So
Yeah.
27 equals to negative 9 times a sub 7. Therefore, the leading coefficient is negative 3. And the full function is now fx equals to negative 3 times x cubed times x plus 2 squared times x minus 2 squared. And how do we graph this? How do we graph this? The y-intercept is 0, 0. Actually, the x-intercepts are 0, 0, 2, 0, negative 2, 0. This is degree of 7, which is odd. And the leading coefficient is negative. So the sign graph will be as the following. 0, 2, 0 here, 0 here, 0 here. Oh, we know f negative 1, huh? F negative 1 is what?
27.
27. So when x equals to negative 1, that's 27, that's positive. And negative 2 is a 0 with even multiplicity. So what's the sign here?
Positive?
Still positive because negative 2 is a 0 with even multiplicity. How about this one here?
Oh. Negative.
Why?
Because of the exponent.
The exponent is
Even. I mean odd.
it's odd, therefore it changed sign. So if the multiplicity of the critical number you pass is even, you don't change sign. If the multiplicity of the critical number you pass is odd, then you change the sign. Now, with that notion, knowing that 2 is a critical number with even multiplicity, then it stays the same negative. Now then from here we see that, oh, by the way, notice that when degree is odd and the leading coefficient is negative, then the graph will look like this. I wonder if you remember. Yeah, of course we don't know what happened in the middle, right? Okay, so from positive infinity, when it touch negative 2, bounce like that. This is not supposed to be sharp. So it bounce here and then go up and then goes to 0. By the way, what is the multiplicity of x equals to 0?
3.
3. Now, therefore, when it cross that, we know it will change sign, right? So when it will cross like an x cube. Okay, it's not going straight. No, it's going straight if the multiplicity is a single multiplicity, like multiplicity of 1. If it is multiplicity of 3, then it will behave like x cubed surrounding the critical numbers. And here, because the multiplicity is 2, it will behave like x squared in surrounding the critical number here. Likewise, now then when it touch that 2, it will behave like x squared also. Yes. That will be the graph. Okay, now do you notice that we already combined whatever we know about graphing, factors, factor theorem, and here we also implicitly learn to do more advanced FOIL method. Now we will go on to the material that we have not learned yet. There are more here that you can do though, but the way I think is you can just see from what I taught you earlier to do the graphing. So from the graph, can you find out the polynomial, for example? Okay, let's see more. Suppose, for example, I do number 28. Number 28. We have this polynomial fx equals to x to the 4th minus 9x cubed plus 22x squared minus 32. Now, in future, so basically after today, we need to know how to factor this and graph this function. At this point, we don't know how to do that yet. That's why they help us with telling us 2 zeros. They say that the zeros, 2 of the zeros are 4, and it is with multiplicity of 2. It means x minus 4 squared is a factor. Everybody okay with this?
Yes.
Okay, now, but knowing the factor doesn't help us right now. What we need is we will use the zeros to reduce the polynomial. Now, I showed you this last time, but I'm not sure if you really see the relation. So let me make it more explicit. So our polynomial have degree of 4. The leading coefficients is 1, negative 9, and then negative 9, and then 22x squared, 0x, negative 32. Now I will use the first 0, 4, to reduce this polynomial from degree of 4 down to degree of 3. Now, because 4 is a 0, I expect the final answer here will be 0. The remainder is supposed to be 0. Okay, but let's see. So this is 4, negative 5, negative 20, 8, 32. Okay, so it means our fx is now, I can factor x minus 4 out, which we expect. We know that I should have x minus 4 squared, right? But knowing x minus 4 squared doesn't tell us what's the remaining factor. So I use one of the 4. Now I reduce that to x minus 4, and then x cubed minus 5x squared plus 2x plus 8. Is it right? Now then I will reduce this again. because 4 is a 0 with multiplicity of 2. So I already reduced by x minus 4 once. I will do it again by 4. Now you see that I can update my function into partially factored form. This first x minus 4 comes from here. Oops. It comes from here. While this guy here now becomes x minus 4 times x squared minus x minus 2. Do you see that?
Yes.
Now, because it is degree of 4 originally, and then I know 2 of the zeros, it means I just need to find 2 more zeros. And those 2 more zeros should come from here. Now, but actually at this point, I can factor it already. I believe that's factorable. So these 2 guys here give us x minus 4 squared as we expected. We knew it earlier, but we need to use those 2 zeros to find the factors and the remaining zeros. This will give us x minus 2, x plus 1. Now you see that once we write them in factored form, we can actually graph them already. Yeah. The question in this number 28 only asks us to write it in as a product of linear factors. But suppose we already write them in product of linear factors, then we can go on graphing it. First, the sign graph, -1, 2, 4. I will do it fast, so you can chew it later. This is positive. This is positive. Positive. Negative. Right. Hold on. From the constant term, I know that the y-intercept is 0, -32, right? And you can use that information actually here. When x equals to 0, the y is -32. And then you do that business that -1 is a 0 with multiplicity of 1, so I change sign. 2 is a 0 with multiplicity of 1, so I change sign. 4 is a 0 with even multiplicity of 2, I keep the sign. Now then, using that information, using the sign graph, now we go on even further. When we sketch the graph, so this is x-intercept here, we have x-intercept here, we have x-intercept here. And then the graph, oh, hold on. When x equals to 0, what's the y again? -32. So the graph will be approximately, let me use different color. It will be approximately like this. And notice that x equals to -1, x equals to 2 are both zeros with single multiplicity. So when they cross the x-axis, it will cross linearly. While at 4, it's multiplicity of 2, so it will behave like x squared surrounding the zeros there. Okay. Now, I will not go on further from here. Just to show you that if we know some zeros of a polynomial, we can use those zeros as a bait to reduce the polynomial. Hopefully we can reduce that down to degree of 2, like what we did earlier here. It's originally degree of 4, right? But I have 2 zeros. Now I will use I use these two zeros then to reduce this polynomial to the factors that we know, x minus 4 squared, and the remaining part here, then because it's degree of 2, then I should be able to factor it. In case we cannot factor it, we can use quadratic formula or completing the square method. Now, the new material. From our lecture video, important one, Descartes' rule of sign. This person, as I know, is a French, so we're supposed to read this as Descartes' rule of sign. But anyway, I read that as a Descartes' rule of sign. Just let you know, this guy who invented this rule of signs is the same guy who invented the Cartesian coordinate system. So I hope you realize that among all these theorems that we have here, among all the theorems that we learn in this chapter 3, this rule of signs is the oldest one. Okay, so somebody long time ago, for some strange reason, find these rules. Our textbook shows the proof. I will just give you the statement and the application of this. The lecture video I gave you yesterday, I posted in the announcement, I believe. Also just give you the statement of the Descartes rule of sign and the example. Okay, let's see the statement. Descartes rule of sign says the following. Let Px be a polynomial in descending order. Which means the exponent is from the highest to the smallest. Now, let's define the variation of signs, the number of variation of signs is the number of times the sign change either from positive to negative or from negative to positive. Let's explain this a little bit. For example, if I have Px equals to 3x to the 4 minus 5x cubed minus 2x squared plus 7x plus 10. Then the number of times the sign changes, which we call the variation of sign, is the times that the coefficient change sign from positive becomes negative or negative becomes positive. Okay, so positive becomes negative, that's one time. Negative becomes negative, there's no change of sign. Negative becomes positive, there is change of sign. Positive becomes positive, there is no change of sign. So the variation of signs here is 2. Is it okay? Now that's for a variation of signs. Now let me erase this to this from our way so that we don't get distracted. I can actually also. Oh, by the way, the polynomial I showed you earlier, you can review it on the recording later on. The polynomial I showed you earlier, already in descending order, the exponent starts from the highest and slowly goes down to the smallest. Okay, now let Px be a polynomial. Then we go back to the statement of Descartes of Descartes rule of sign. First part, the number of positive zeros. Notice that this will give us also the number of X-intercepts later on, or to the right of y-axis. Up to multiplicity. So later on, when we try to graph that, we want to find out how many X-intercepts up to multiplicity happens on the right-hand side of the y-axis. Okay, now the number of X-intercepts to the right of the y-axis can be seen from the number of positive zeros, which is given by the number of variational signs or that number subtracted by an even number, a multiplicity of 2, a number subtracted by an even number. Let's say, for example, Descartes' rule of sign consists of 2 parts, but once we understand the first part, the second part is easy to see. Okay, suppose I have the one that I had earlier, I forgot, by the way. Let me just make it up again. 4x to the 4 minus 5x cubed minus 7x squared plus 2x plus 10. This is the px, right? Now, how many times the sign changes? Change 1 time here. It doesn't change here. It changes again 1 time here. Okay, because it happens twice, then px has 2 positive zeros or that number, which is 2 subtracted by an even number, or if I subtract these 2 by a multiple of 2, I will get 0 or no positive 0. Now, in other words, either we have 2 X-intercepts on the right-hand side of y-axis or nothing at all. Now, let's see another example. This time, let me pick an example from our book. Let's say I see number 38. I have this function fx. Oh, no, it's not a function. Okay, that's an equation. The question is how many positive zeros or how many positive solutions for this polynomial. Then we see, if we see this, the left-hand side here as our polynomial, then this equation basically to find the solution or the zeros. Now, if we wonder how many positive solutions here, positive roots or positive zeros, then we see how many times the sign changed. One time here, another one time here, another one time here, another one time here. So then we say the equation has 4 or 2, which is that 4 subtracted by 2, or 0. From that 4 minus 4, I get 0 positive solutions. Because it has 4 times, the sign changes 4 times. So it either has 4 positive solutions or only 2 or no positive solutions at all. Okay, now that's for the first part of Descartes' rule of sign. The number of positive zeros of Px is equal to the number of variation of signs, or that number subtracted by an even number. Now, how about the second part? The second part of Descartes' rule of sign, wonder about how many negative zeros we have. We wonder the number of negative zeros we have. The number of negative zeros. Now, by the way, just to remind you, this will give us the number of negative X-intercepts. Or to be more precise, the number of X-intercept to the left of y-axis. So instead of on the right-hand side, this will give us the number of X-intercept on the left-hand side of y-axis. Now, the number of negative zeros of a polynomial is equal to the number of variation of signs of p negative x. Now, basically what Descartes doing at that time, what Mr. Descartes did at that time, he reflected the graph of this polynomial respect to the y-axis by replacing x by negative x and see how many times the sign change of the resulting new polynomial. Okay, the number of variation of signs of p negative x, or that number subtracted by an even number. Okay, let's this time apply both of this idea into a more concrete example that we already know. Suppose I have px equals to x squared minus 5x minus 6. Now, how many positive zeros? Then we see how many times the sign changes. Positive 0, positive
1.
0, that will be 1. And we see that from here, there's only one time, right? So 1 positive 0, which if we subtract by 2, it's already negative. So we cannot have negative number of zeros, of course. We have 1 positive zeros, which also means that we are guaranteed there must be 1 positive zeros. There must be 1 x-intercept to the right of y-axis. Okay, now, and then let's take a look on what happened if we observe p negative x. P negative x That's negative x being squared minus 5 times negative x minus 6. That will be x squared plus 5x minus 6. Now then, let's take a look how many times the sign change. The sign change only one time, right? So the number of negative 0 will be also only 1, right? So we have one positive 0 and one negative 0, which implies we have one x-intercept on the right-hand side of y-axis and another one x-intercept on the left-hand side of y-axis. Now, the reason I picked this example is because we know we can find the x-intercepts, which means the zeros. We need to first find the zeros by factoring, by simply factoring it. If I factor this, 0 equals to x squared minus 5x minus 6, x minus 6, x plus 1, so x equals to 6, x equals to negative 1. Notice that we have one positive 0, which is x equals to negative 6, and another one negative 0, which is x equals to negative 1. Now, if I sketch this, notice that the y-intercept is 0, negative 6, x-intercepts are negative 1, 0, and 6, 0. You see here that we have one x-intercept on the right-hand side of y-axis and one x-intercept on the left-hand side of the y-axis. The graph is approximately something looks like this. Is it okay? Now, let's look back to that number 30. Number what? Number 38. Number 38. Go back to that number 38. We already have the positive zeros. How do I do this? I already have the number of positive zeros. The equation has 4, 2, or 0 positive zeros. Now let's take a look what happened if I replace the x by negative x. So let's say the px here is 2x to the 4th minus x cubed plus x squared minus 3x plus 4, then p negative x will be replacing the x by negative x. Which simplifies to be 2x to the 4th plus x cubed plus x squared plus 3x plus 4. Now, how many variation of signs here? Hello?
No.
There's no variation of sign?
Zero.
Okay, so the equation has 0 negative solution. Okay, now I usually only talk about the number of positive solutions or negative solutions, but from there we can also find out all the possible variations and therefore find how many complex solutions. From fundamental theorem of algebra, we know that the number of solutions this polynomial, this equation supposed to be 4. There should be 4 solutions. Okay. Now it is possible that all 4 are positive. It is possible only 2 of them positive. But if 2 of them positive, the thing is like if we have this case, it has two positive solutions and 0 negative solutions. It means how many of them complex solution?
2.
2, because the total number of solutions should be 4, right? Okay, now
Mhm.
before I give you a break, let me give you something nice. I want to graph this. By the way, do you see my graphing plane here? Anybody? If not,
What?
then I need. Do you see my graphing paper here?
No.
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 Let me show you that. A second. Share screen here. This is the one. Do you see that now?
Yeah.
Okay. Regan, this is the software that I was actually supposed to give you, but you give me your.
Yeah.
But I don't know how to give it back right now. Okay. Let's see. Oh, what is this? Oh, okay. So y equals to 2x to the 4, and then minus x cubed plus x squared minus 3x plus 4. This is what the graph looks like. So how many x-intercept do we have here?
2.
How many?
0.
Mhm.
There's no x-intercepts, right? In fact,
Yes.
yeah, there's no x-intercept, not even positive x-intercept. So the case that we have from, give me a second. The case that we have earlier here, we actually have the case of no positive solutions and no negative solutions. So the one we have was not this blue one. Let me erase that. Not this case, but the one we have actually this case, no positive solution, no negative solutions. So all 4 are complex solutions. Okay. Now in this situation, then we say this solution, this equation has no real solutions because it's no positive, no negative, then no real. All of them are complex solutions. Okay. Now it doesn't violate fundamental theorem of algebra because it still have 4 solutions because it's degree of 4, but all those solutions are not real. They are complex numbers. Okay, let's take a little break here. Let's come back at, right now it's 10:51. Let's come back at 11 o'clock. Will that be fine?
Yes.
Yeah.
Okay, let's come back at 11 o'clock. Let me pause the recording and see you later at 11.
Okay.
3.4 is about what? Let me see the title. Rational zeros of polynomials, complex and rational zeros of polynomials. Okay, let's start. A couple things. First one is fundamental theorem of algebra. This is one of the theorem that is so fundamental, but at the same time, it's the easiest one, which actually says that let polynomial px be a polynomial of degree n. Then Px has n zeros. Of course, the complete statement supposed to be Px be a polynomial with real coefficients. Which I don't think that's necessary though, but I saw some people actually put it in. That's why I didn't insert that there. Okay, of course, in this course, we will deal with polynomial with coefficients, real numbers. Okay, in fact, I try my best to have a polynomial with coefficients, integer coefficients. Now, this theorem, however, has some variation, some people say it another way. It says that let Px be a polynomial of degree n, then Px has at least 1 0. But it actually has n zeros. Now, basically, if you have a polynomial degree n, then we should have n zeros. Now, these zeros may, all of them becomes x-intercepts, but if the zero happen to be a complex number, then it won't be. It won't be an x-intercept. It won't show up on the graph. Now, that's fundamental theorem of algebra. Some insert, some extra. The number of turning points for the graph of Px is at most n minus 1. Now let me ask you to write it down first. I'm not sure if our textbook actually mentioned this. Let me give you the view of my software earlier. Let's say we have 2x minus 4 or 2x minus 3. Now, what is the degree of this polynomial? Do you see this?
Linear?
Yeah, that's linear function, right? So the degree is
1.
1. Therefore, according to what I just said, the number of turning points, then the number of turning points is at most 0. In other words, we don't expect to see any curve anywhere it turns. Now you see, linear functions, as we know, has no turning points. Then, what happens if I change this to be x squared minus 3x, maybe plus 7. Oops. Minus 3x plus 7. It does not have x-intercept, but that's not the issue here. We do see one turning point. The turning point is actually here.
Mm-hmm.
This is the turning point, right? Okay, you see degree is 2. The degree of 2 has at most 1 turning point. Let me change that exponent becomes the degree of 3. Then we will expect to see at most how many turning points?
2.
2. You see, we have 1 turning point here and another turning point here. Okay, now when I say turning points, it seems like refers to this point where you have local maximum, local minimum. Of course, these are turning points, but this is also turning points, by the way. imagine if I deal with x cubed only. X cubed, we expect to see at most, according to that statement, it should have at most two turning points, right? But here we have only one turning point. We have only one turning point here. Okay, yeah. In fact, even though I have one turning point, how many x-intercepts here?
Just one.
Just one. What is the multiplicity?
3.
3. Is it okay? Now that's for that number of turning points. Let me go back to our main screen. Fundamental theorem of algebra is, in my opinion, the easiest theorem, actually, maybe for the whole semester. Let me go on. Then another theorem comes up. Well, it doesn't really take long. The next theorem, conjugate zeros theorem. Conjugate zeros theorem. Some textbook or some lecture videos I saw, they call it conjugate pair theorem. It says the following: if a zero of a polynomial, I think I should say, yeah, a zero of a polynomial is of the form a plus square root of b, then its conjugate is also a zero of px. Now the conjugate of a plus square root of b is a minus square root of b. I have to emphasize that the b here is not a square number. Okay, so for example, if I know, 3 plus square root of 2 is a zero of a polynomial, then 3 minus square root of 2 will also be a zero of a polynomial. Are you with me? Now, conjugate is we have, if we have the situation like this in which they only differ by the sign in the middle. Okay, now the thing is, when I try to find the lecture videos online, a lot of those instructors, I cannot find anybody that quote the conjugate zero theorem correctly. All of them talk about conjugate zero theorems in terms of complex number, a plus bi and a minus bi, which is true. But conjugate zero theorem is actually larger than just for complex numbers. No. Now, you notice that a plus bi is actually a plus b square root of -1, right? Or we can say that that's the same to a plus square root of -b squared, if you think about it, right? But notice that even though I have b squared inside, but because of the negative, that's not a square number. Let's say, for example, if I have 3 plus 2i. Now, that's a complex number, and it has a conjugate. Now, then the conjugate must also be a zero. Now, that's what a lot of those lecture videos says, which is true. Don't get me wrong, they are true. But the one that we need is actually the irrational version of that. If an irrational number, 3 plus radical 2, for example, is a zero, then the conjugate is also a zero. If you remember, one of the questions we did earlier in 3.2 3.2 or 3.3, as I remember, it says that a polynomial has 3 zeros, negative 3i, 3i, and 0. I wonder if you remember that. 3.3, as I remember, that's number 6, maybe. I don't remember. Okay, now I want you to notice that negative 3i and 3i actually conjugate to each other. They are conjugate to each other. That's 0 minus 3i. Now, once 0 minus 3i is a 0, then 0 plus 3i must also be a 0. Buy one, get one free. Is it okay? And we have seen this phenomena actually a lot in when we solve quadratic equation. Notice that, let's say if I have x plus x squared plus 4x, maybe minus 5, maybe minus 6 instead, equals to 0. Then x squared plus 4x equals to 6. X squared plus 4x plus 4 equals to 10, right? So x plus 2 equals to plus minus square root of 10. So x equals to negative 2 plus minus square root of 10. Notice that the solutions are not rationals, they are irrational. Okay, and when we split them, we write it in term by term. Negative 2 square root of 10 is a solution, but because that's an irrational, then the conjugate negative 2 minus square root of 10 must also be a solution. Okay, now that's the key of this conjugate zero theorem. Next, rational zero theorem.
Okay.
Let Px be a polynomial with leading coefficient a sub n and constant term a sub 0. Then, if C is a rational 0, of Px, now number is rational is when we can write it as a fraction. Oh, you know what? I'm sorry. I have to emphasize one more thing that I have skipped in the hypothesis. It's a polynomial with integers coefficients. Integer coefficient. Emphasize that. So the coefficient of that polynomial has to be all integer. Then, if C is a rational 0 of Px, which means that 0 is a number in form of a fraction, then C must be plus minus a factor of constant term or divided by a factor of the leading coefficient. Now, let's have some instinct of this first. Suppose, for example, I have this polynomial Px equals to 3x squared minus 10x plus 3. We can solve this by factoring, right? But let's solve this first. Let's solve this. This is 3x minus 1, x minus 3. So the zeros are 1/3 and 3, right? Now notice that this 1/3, the 1 is a factor of the constant term. This 1 here is a factor of constant term. And the 3 on the denominator is a factor of the leading coefficient. Now likewise, the 3 here, which I can write as 3 over 1, the numerator is a factor of the constant term. And the 1, the denominator, is a factor of the leading coefficient. Okay? Now, as long as the solution, as long as the zeros, as long as that 0 is a rational number, then it must be, the numerator must be a factor of constant, and the denominator must be a factor of the leading coefficients. Now, how will this help us later on? That will give us the candidates for solving a polynomial, or finding the zeros of a polynomial. Let's say, for example, I pick number, let's see. I want to find the easy one, but not too easy. Maybe number 26. Number 26. Okay, I modified the question a little bit. Number 26, I have 3x, oops, sorry, 3x to the 5th minus 10x to the 4th minus 6x cubed plus 24x squared plus 11x minus 6. Now suppose I try to find the zeros of this. Basically, when we say find the zeros, basically I want to solve this equation here. Okay, when px equals to 0, what are the x, right? Now then, at this point, because this is degree of 5 already, we have no way to factor this directly. What we can do guessing. And if we need to do guessing, we would like to know which number to guess. Okay, now, so according to the rational zero theorem, if C is a zero of the polynomial, then C must be a factor of the constant over a factor of 3. Okay, so that's plus minus the factor of 6 are 1, 2, 3, 6. And a factor of 3 is 1 and 3. Now then, what are the possible rational zeros of this polynomial? It's 1 over 1, which is
1.
1, 2 over 1,
2.
2, 3 over 1,
3.
6
and
over
6.
1, 6. Give me a second, I saw some question. Oh, great. Now then, what happens if I do over 3? So I have 1 over 3. And then 2 over 3.
2/3.
Now 3 over 3,
That's 1.
which is 1. That's the same. We already have
We
it,
have it.
right? So I will erase that, okay? So I will erase that. And likewise, 6 over 3 is
2.
2, which I also already have. So right now I have how many candidates? If I have any rational zeros, and those are 1, 2, 3, 6, 1/3, 1 and 2/3 with the plus minus. So there are 1, 2, 3, 4, 5, 6 times 2 possibilities.
12.
There are 12 possibilities. Okay, now we know it should have only 5 zeros though. We know it should have only 5 zeros, right? If we combine with other method that we learned before, then we can actually narrow down more and more and get the actual zeros, and we can factor, get more zeros from there. Okay, now go back to that rational zero theorem. Rational zero theorem says that if you have a polynomial with integer coefficients, so the coefficient has all to be integer, no fraction, no irrational number, no complex number. Here we have integer. Now, what happens, Thomas, if I have fraction, for example, then I will multiply by the LCD to get the integer coefficients. Okay, now, let me summarize everything we learned so far. I think that's enough. Our textbook actually mentioned something else called boundedness theorem. If you can read that yourself, that will be great. I saw boundedness theorem in 3.3, but I will actually mention about boundedness theorem when I do those problems. Let's summarize what we learned so far. I have only half an hour left, and I try to put things together. Okay, what are the theorems we have learned so far? The most important theorems to apply. So I see some chat. Is long distance theorem on the same chapter? What long distance theorem? Oh, no, it's not long distance, theorem. Boundedness theorem. Yeah, boundedness theorem is in 3.3. I will not teach you explicitly. I will teach you on the way. Okay, let's come back here. What are things we need to remember? The first one, the easiest one, is fundamental theorem of algebra. Basically, number of zeros equals to n, equals to the degree. The second, in my opinion, help us to reduce the search later on. So none of the, I have to emphasize this, none of the theorems that we learned so far, including the rules, actually tell us exactly what are the zeros. It's not like a quadratic equation, polynomial, that we can just factor it, or we can just use formula and get the exact zeros right away. Once it's the degree is more than 2, 3, 4, 5, 6, and on, then there's no method that we can use to pinpoint the zeros directly, no. But we have a bunch of theorems to help us narrowing down the options. Okay, now fundamental theorem of algebra tell us how many zeros we need to look for. So if we have degree of 3, you don't need to look for the 4 zeros or 5 zeros. Once we have 3 zeros, we are good. Okay, second, Descartes' rule of sign actually help us to narrow down from the n number of zeros that we're supposed to be, how many of them positive, how many of them negative, and therefore how many of them complex. Is it okay? That's what Descartes' rule of sign doing. Now, so if we know that according to Descartes' rule of sign, we have 2 positive and 1 negative, even though the degree is 5, then once I get 2 positive zeros, I stop. I don't need to go to find the 3rd one or the 4th one. Okay. Now, this Cartesian sign tell us the breakdown further breakdown from the number of zeros that we have, how many of them supposed to be positive, how many of them supposed to be negative, and therefore we know when to stop. Next. The next important one is rational zero theorem. Rational zero theorem. Rational zero theorem help us to see that if I need to try, if I need to guess what are the zeros, then I guess it first using rational numbers. Okay, like imagine if I have a polynomial like this fugly polynomial here, and you ask me to graph it. Now, to graph this fugly polynomial, I need to first factor it. But when I factor it, I need to find the zeros, of course. When I try to find the zeros, I will not start with complex numbers. Are you with me?
Mm-hmm.
Right? We will start with guessing, but when we guess, we don't randomly guess numbers like, oh, you know what? Let me guess that. Let me try 4. Let me try 7. No, no need. Why? Because we know from rational zero theorem, 5 will not be a 0, 7 will not be a 0. Does it make sense?
Yeah.
It doesn't tell us the answer, but it tells us what cannot be the answer. Does it make sense? Okay. Now, in fact, of all this theorem here, in my opinion, rational zero theorem is the most important one. What else? Of course, using rational zero theorems, then we have in between we have remainder theorem. Synthetic division. Intermediate value theorem. Now, what I meant is the following. When I try a number as the candidate of 0, let's say if I go back to this polynomial, I will work on this polynomial later on, number 26. Okay, let's say I go back to this polynomial and then I say, you know what, let me guess that 3 is a 0. Okay, now, and it turns out 3 is not a 0. Even though it is not a 0, but we may be able to use that using the remainder theorem and intermediate value theorem to narrow down our option. Okay, and then we together with this group is actually factor theorem. Okay, now let me start clean. I will quote this and start on the new page. Not this one. My bad. My bad. My bad. Not this one. I should copy this first and then go here. Now, let's start this with this polynomial again, number 26. Suppose I want to find all the solutions, all the zeros. Oops, when I erase this, I erased it. Can anybody help me? What's the coefficient here? It's a 3. And this is a 6. Did I miss anything? And this is 24. Okay, now let's say we start from this polynomial. Let's find out the easiest one first. What is the y-intercept, by the way?
0, negative 6.
0, negative 6. Now, to find the x-intercepts, I need to find the zeros. To find the zeros, I need to factor them, right? Okay. Let's go back to easier question then. How about the domain? It's a polynomial, so the domain will be all real numbers. for this question, I happen to be able to ask what's the range. Why? Because the degree is odd, right? If the degree is odd, then either the graph look like this, from negative infinity on the left-hand side to positive infinity on the right-hand side, or from positive infinity go to negative infinity. If it is degree of 5. In fact, we know the leading coefficient is positive.
It's positive. It's the first one.
Must be the first one. But either way, because it goes to negative infinity when you go to the far left, it goes to positive infinity to the far right, and the domain is all real number. Then the range must be all real number
All
also.
real number.
Yeah. You will see that this is the case if the polynomial has an odd degree. If the polynomial has an odd degree, then the range must be all real numbers. Okay. Now then, let's apply what you know, the Descartes' rule of sign. Can I ask you to see how many positive zeros this polynomial have? Change one time here, another one time here, another one time here, right? So there are 3 or
1
positive zeros. Now, in other words, even though we know that this polynomial have 5 zeros, only 3 of them will be positive. Okay. Now then, how about negative zeros? To find negative zeros, we need to first observe p negative x. That's 3 negative x to the 5th minus 10 times negative x to the 4th minus 6 times negative x cubed plus 24x, negative x squared plus 11 times negative x minus 6. Okay, let me ask you to work it out. Then this will be negative 3x to the 5th minus 10x to the 4th plus 6x cubed plus 24x squared minus 11x minus 6. So how many times it change? One time here and one time here. Okay, so it will have either 2 or no negative 0. By the way, in your test, I need you to show me this. I need you to show me this. I need you to show me this. At least this one here. At least this one here. With some practice, you will notice that the sign will change if the exponent is odd. If the exponent is even, the sign stays the same. If the exponent is odd, you change the sign. Okay, compare that with the original polynomial. Compare that with the original polynomial. Degree of 5, you change the sign, becomes negative. You see that? Right? Degree of 4, you don't change the sign, it stays negative 10. Degree of 3, because it's odd exponent, then when you replace x by negative x, it will change the sign, and so on and so forth. Okay? But if you don't know what to do, you just go ahead with doing it long way. Okay? Now, so we know that it will have either 3 positive zeros or 1 positive zero. And for the negative zero, either 2 of them or none of them. Now, next one. How about the rational zero theorem? Rational zero theorem. if C is a rational 0, then it must be a factor of 6 over a factor of 3. Now, in your test, I need you to list them correctly. Plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 1/3, plus minus 2/3, plus minus 3/3, which is 1. We already have that. Plus minus 6/3, which is 2. We already have. Is it okay? Now, then, once I have the candidates that I get from the rational zero theorem, then I will try to find the zeros. So, that's our polynomials. Find all zeros of Px. Now, in your test later on, you will do a lot of work from this part here on your scratch paper. So let me show you how I will do it on my scratch paper. I will do the guessing. Let's see, what is P1? P1, just especially for 1. If I add the coefficients, do I get 0? That's I get 38 minus 22. 16? Possibly 16? Is it okay? Oh, by the way, that's something nice though, because I also know the y-intercept P0 is -6. Do you notice that? Which means, according to intermediate value theorem, there is a 0, at least a 0 between 0 and 1. Is it okay?
Mm-hmm.
Okay, I don't know what's that, but we will check either 1/3 or 2/3 later on. Okay, but I will do it later. I will do it later. Let's do something else. How about if I want to find P2? Let's see if I want to find P2 this time. I don't want to plug that in. I use synthetic division to find P2. Oh, P2 is a 0, huh? Right? P2 is a 0. So then, because P2 is a 0, I will copy this work here in my main paper, on my test paper. So 3, -10, -6, 24, 11, -6. Those 2, 3, 6, -4, 8, -14, 3, 6, 0. So I already get to a 0 And therefore, instead of dealing with degree of 5, now I deal with degree of 4. Is it okay? Now, is it possible that 2 is another 0? Let's say, for example, is it possible that 2, now we see 2 is a 0, right? But it happens only once so far. Is it possible that 2 is a 0 with multiplicity of 2? And can 2 be another 0 from here? Can 2 be another 0 from this polynomial? The answer is no, because according to rational zero theorem, factor of 3 over factor of 3 cannot include 2. 2 is not in the list.
Okay.
Right? If I update my rational zero theorem right now, if I update my rational zero theorem right now, then it will be a factor of 3 over a factor of 3. Are you with me?
Yeah.
So if we look back to our rational zero theorem that we applied earlier, once we get 2 is a 0, now 6 cannot be. I already eliminate this right now.
So you eliminate them.
Yeah, so right now I have only plus minus 1, plus minus 1/3, plus minus 3, right? Let me try 3 then. Let me try 3. Let me try 3. Let me do it here. Let me erase that first. Okay, let me try 3. Now when I try 3, I can just continue from here. And hopefully at the end on the solution here, I have 0. But I never know. Let me try it first. 3 times 3 is 9. This is 5. 15. This is 1. This is 3. Negative 1 times. Oh yeah, that's 0. Okay. So 3 is also a 0. Haha. Nice, right? You know what? I just continue. I can only continue this way if the remainder is 0. Okay, if not, then it's not a 0. I cannot continue from there. 3, this is 9, this is 5, this is 15, this is 1, this is 3, 1, negative 3, 0. Okay, so I already have 2 zeros right now. In fact, 2 positive zeros, right? 2 positive zeros. How many positive zeros am I supposed to have? 3 or 1. Right? But I already have 2 of them, so it won't be only 1 positive 0. It should be 3. I need to look for the other one. Now, can you help me using what I see here? Can you update your rational zero theorem?
It has to be 1/3 or negative 1/3, right?
Yeah, 1/3 or negative 1/3. I suspect it is 1/3 because from our what we have here, P0 and P1, there must be a 0 between 0 and 1, right?
So that's positive 0, right? So it's negative. So it's 1/3.
Yeah, 1/3. But that's still very likely though. Okay, we don't know. We don't know for sure. Okay, but let's try. Let's try. Let's try here on my scratch paper just to confirm. Yeah, it's 1/3. So 3 times 1/3, that's 1. This is 6 times 1/3, that's 2. 3 times 1/3, that's 1. Oh yeah, that's right. Okay, so I already get another 0, which is 1/3. That's 3, 1, 6, 2, 3, 1, 0. Now, we already have 3 positive zeros, right? We already have 3 positive zeros. That's the maximum number of positive zeros, agree? So if there's any more zeros, it won't be positive. It must be on the negative side. Are you with me?
Mm-hmm.
Okay. Now, that's one thing. Second thing to say is that the other two should be negative or complex zeros. Okay. Now then, but on the other hand, what is the degree here?
2.
That's the degree of 2. So we can now update my polynomial to be x minus 2 times x minus 3 times x minus 1/3 times 3x squared plus 6x plus 3. Is it right?
Mhm.
Okay. Now, by the way, before I go on too far, even if I did not notice about this intermediate value theorem here, you are actually still fine. You can have this 3, 5, 1, -1 here, right? Without that 1/3. And you can try to look for the negative zeros. You can try maybe -1, for example. Okay. Yeah, you can try -1. So you don't need to get this 1/3 to fully solve, to fully factor it. As long as you can find a zero, then another zero, you can actually fully factor it already. Now, let me go on here. I happen to be lucky that I can guess this 1/3 nicely. Okay, but let me factor the 3 out first. So 3 times x minus 2, x minus 3, x minus 1/3, x squared plus 2x plus 1, which I hope you see that you can factor directly. It's already degree of 2, right? It's already degree of 2. So this is 3 times x minus 2, x minus 3, x minus 1/3, x plus 1 squared. Okay, by the way, I need you to realize that this is actually what we call the linear factor. Linear factor form of Px. The reason is when we factor it, all of them becomes linear part. This is linear here, this is linear, this is linear, this is linear. Okay, and all of them with x plus something or x minus something. Not 3x minus something, 3x plus something. No. The leading coefficient 3 has to go up. Okay, now then let me go on. So what are the zeros? The zeros of the polynomials are x equals to 2, x equals to 3, x equals to 1/3, and x equals to -1 with multiplicity of 2. Okay, the ones here are all multiplicity of 1. Agreed?
Yes.
Now, because all of the zeros are real numbers, then we can go on to the next question. What are the x-intercepts? Don't forget, x-intercept, just like y-intercept, has to be written in coordinate form. That's actually the difference between a zero and x-intercepts. Zeros are just numbers, x equals, x equals, x equals, x equals. X-intercept has to be a coordinate, 2, 0, 3, 0, -1/3, 0, and -1, 0. Okay? Now then, once we get the x-intercepts from the zeros, we can do the sign graph. We can do the sign graph. Actually, this is a stepping stone for us to sketch the graph later on. And the sign graph will be 1, 1/3, 2, and 3. What's the x-intercepts again? I mean the y-intercepts?
0, -6.
0, -6. So when x equals to 0, the y is negative?
6.
Yeah, -6. I just need the sign, right?
Yeah.
Okay. Yeah, -6. That's right. So negative. And then using the multiplicity, then I go, this will be between 2 to 3. Positive or negative? What's the multiplicity of this 0?
1
So when I jump across that critical number, I will change sign.
changes.
When I jump across these 3, because multiplicity is odd, I change sign again. Hold on, something not really right. Am I missing something? Am I missing something? Oh, I'm sorry. It's not. I make a mistake. Actually, very big mistake. It should be positive 1/3. Should be positive 1/3. And that's where the mistake starts. So when x equals to 0, x equals to 0 should be here. So this is negative. This is positive. This is negative here. And this is positive. Now, -1 is a 0 with even multiplicity. So when I jump across this critical number, I don't change the sign. Now then, let's fully graph this. At least the sketch. The y-intercept 0, -6. X-intercepts are 1/3, 0, and then 2, 0, 3, 0, -1, 0. Using the sign graph, I know I come from negative infinity. Here, go to negative again, and then go up here. Positive becomes negative times positive. Oops. So approximately that's what the graph looks like. Okay, that's time's up, and that's basically what I need you to do also. I already post on my announcement yesterday what question you should be able to try to work on for your for 3.3 and 3.4. And I also include some problems on my old tests. You should study from there. Start working on those. Okay. And I think later in the afternoon or tomorrow, let's see how lazy I am. I will post some lecture videos for 3.5. Now, 3.5 is a rational function. Even though it's only one section, it turns out to be an actually quite long section. So I expect to spend the whole day on Monday just for 3.5. Now, if you have a chance, please read that. 3.6 is actually on the easy side. If you can read that, it will be great also. But focus on 3.5. I will give you the lecture video to help you see not too much into details. Because when you read the book, they usually go to too much details at first. So lecture video usually give you the brief look, and then after that you may read the book. Okay. Any questions so far?
Can I just see the sign graph for this lesson, please?
Sure. The sign graph that we have earlier, this one. So from negative infinity to -1, it's below x-axis. From -1 to 1/3, it's also below x-axis because it's negative, right? From 1/3 to 2, it's positive, so it's above x-axis. And then from 2 to 3, it's negative, so it's below x-axis. And so on and so forth.
Okay.
I'm recording this lecture video, so in case that you want to review this, what happened is this, because I record it, but I'm not recording it on my computer. They record that on the state cloud. Then after a couple of minutes, maybe 1 hour, they will give me the link to the recording. I will download it and I post it on YouTube. It will take like a couple hours actually to upload it to YouTube. Now, then once I upload it on YouTube, I will also give you the link to on the announcement. Is it the answer? No, on the discussion, huh? On just like the last discussion.
Yeah, right. The last.
Right? Yeah, I have the lecture video there. Basically, what I do here, I post it there. That's for students who cannot follow the lecture today. And I hope that's actually a good practice. Okay, then see you then on Monday. Check the canvas maybe tonight or tomorrow.
Yeah, no quizzes or anything so far.
I will let you know. I will let you know
Okay.
if I have.
All right, that's great.
Yeah,
I'm fine
but
with
if you think about it right now, basically the quiz is basically take home.
There what?
The quiz will be basically take home.
Oh yes.
Right. Okay.
Yeah,
So my quiz later on will more in sense of like a project instead of like a in-class quiz. I will not do in-class quiz anymore. And if you think about it even further, your test basically, I give you the time, the whole period, basically 2.5 hours. But I will not know if you do open book.
Yes.
Right. And I actually don't mind. I don't care. Do whatever you can. Just give me a good result. Okay then. See you on Monday.
Thank you. See you.
Welcome. See you Monday.